Okay, well, I feel like I'm actually rolling now. Okay, so we just did electromagnetic waves that are normally incident on a boundary between two materials. And in this section of the material, we're going to just talk about, I'm not going to work through everything he works through in the book, but I'm just going to go through what I think is the coolest part of it. And and that is I have an electromagnetic wave which is not normally incident, so it's obliquely incident on the boundary between two materials. And so I have my incident wave vector, my reflected wave vector, and my transmitted wave vector. And the wave numbers are going to be determined by the wave speed on both sides as before. So there's the same k values, only they're not in the vectors aren't in the z hat or minus z hat direction for the incident and transmitted and reflected waves, respectively. Okay, so that means that the difference here is that I've got, instead of x hat, I've got n incident, n hat incident. And then for my magnetic field, I've got k incident cross n hat incident. Okay, for the reflected wave, I've got n hat reflected. And then for the reflected magnetic field, I've got k hat r cross n hat r. For the transmitted wave, I've got n hat transmitted. And then for the transmitted magnetic field, I've got k hat transmitted cross n hat transmitted. And so otherwise, you know, the only difference here is that in the previous case, this was x hat, y hat, minus, right, yeah, x hat, y hat, x hat, y hat, right, with a couple of minus signs in there. And also I don't have the minus k hat r minus k, r dot r, but in the previous example, k, the vector k r was minus k1 z again, which is another reason why you would write this down as minus k1 z minus omega t as opposed to k1 z plus omega t. Now, right. Okay. So, right. So what we do is we're going to apply the boundary conditions again at z equals 0. And the boundary conditions give equations of the form, again, the same, it's at z equals 0. The boundary conditions are of the form some constant times e to the I k incident dot r plus some constant e to the I k reflected dot r equals some constant e to the I k transmitted dot r. And this is something that kind of amazes me. This is really like it shows the power of, I mean, in some sense, the power of vectors, right? Because what I've done here, and you'll also note what I've done is factored out e to the minus I omega t from each of these three, okay? Now these must be true for all x and y, because again, the boundary is the xy plane, is the z equals 0 plane, okay? And so these relationships have to be satisfied everywhere on the xy plane. It was trivially true that it would be everywhere, you know, when k was equal to either z hat times something or minus z hat times something. But these must be true for all x and y, including for x equals 0 and separately for y equals 0. And so for x equals 0, what I have then is it's going to be e to the I k, sorry, for y equals 0, it's going to be e to the I kx times x, kix times x plus, you know, and this is going to be e to the I krx times x, and this is going to be e to the I k transmitted x times x, right? And then that relationship that we have with the a plus b plus c and the lowercase a equaling lowercase b equaling lowercase c, that tells me that kix has to equal krx and has to equal k transmitted x. And kiy has to equal kry and has to equal kty, k transmitted y. And that's just from taking that relationship that we had and applying it on the line, on the line y equals 0 and applying it also on the line x equals 0, these relationships have to be true, okay? And so once we have this, we can orient the x-axis so that kix equals ki and kiy is equal to 0. And then what we have then is all the ky's are equal to 0, right? And that means that k incident, k reflected, and k transmitted are coplanar. They're all in the xz plane. And we're getting that just from thinking about how this relationship can be true, given that x and y vary in these exponents, right? Which is, I mean, again, I think that's it's a pretty amazing conclusion, but not as amazing as what we're going to get. Now, what I then get is kix has to equal krx, okay? But what that means is that ki sine theta I has to equal kr sine theta r. But ki equals kr because that's just the wave numbers, right? And that tells me that the sine of the angle of incidence is equal to the sine of the angle of reflection, which tells me that fundamental result from optics, which is the angle of incidence equals the angle of reflection, right? And again, I'm just getting this by thinking about what must be true in order for this general relationship that has to be there because of the boundary conditions for that to be true. The third thing I get from that is that the x component of the incident wave is equal to the kix is equal to ktx. And so what that tells me is that ki times sine theta I is equal to k transmitted times sine theta transmitted. But k is equal to 2 pi over lambda, which is 2 pi over v over the frequency, which is equal to omega over, which is equal to the angular frequency divided by the wave speed. And that tells me that 1 over v1, because omega is the same on both sides of the boundary, that tells me that 1 over v1 sine theta incident is equal to 1 over v2 sine theta transmitted. Or that tells me that n1 sine theta incident equals n2 sine theta transmitted, where n is the index of index of refraction. So that's, and again, we're getting all of that just from this relationship having to be true. So we've learned a lot. We've learned that ki, k reflected, and k transmitted are coplanar. The angle of reflection equals the angle of incidence, and Snell's law. So I think that's pretty amazing. We could go further, but time is short, okay? And so you can match the boundary conditions like we did before, right? And then get Fresnel equations. And I would just brush over those in the book if I were you. I mean, I'm not going to be testing you on it or giving you an assignment on Fresnel's equations. But if you look at Fresnel's equations, what you're doing is you're talking about the transmitted and the reflected wave amplitudes, right? And then you can see that the amount of energy, the amount of transmitted, the wave amplitude of the transmitted signal is highly dependent on the angle of incidence. And then you leads to things like total internal reflection and all of these basic concepts. And so all of that comes from just matching the boundary conditions for the electromagnetic waves at an interface between two materials. And so that's what I have for Wednesday's lecture. And again, sorry about the kerfuffle because I had that problem with my tablet, but I think we're rolling again now. And I'd say look at these on YouTube, but you're going to have to see them on YouTube in order to hear me say that. So see you on Friday.